Hello, Physics Nation. My name is Nate Larmond, and I'd like to make the threads on a screw. That is, convince you that a right triangle wrapped around a central axis is indeed a screw. Oh, hang on. You see the magic happening right there? The hypotenuse becomes the threads. Whoops. Anyway, you're going to make a few right triangles. So first step is to get a ruler. And what did I do here? A height of 2 inches and a hypotenuse of 4 inches. If you have that right triangle, then this angle right here is a 30-degree angle. So the point of this is to sort of convince you that this side, the adjacent leg, is the circumference of the circle, and this side is the linear motion. That is, as you turn the circle, the cylinder goes up and down. So we're trying to equate this, the adjacent side, to the circumference, and this, the opposite side, to the pitch, the linear distance move for one rotation. So it's easy to do it with a right triangle. Opposite divided by adjacent is tangent of theta. Tangent of theta is 0.577. So just to double check our math, you can find the adjacent leg of this right triangle by doing 2 divided by 0.577, and that's roughly 3.5. And if you put a ruler on this right triangle, it really is roughly 3.5 inches long. So, pardon my scrolling, let me zoom in a little bit here. Like I said, it's this proportionality that's sort of the secret to this. The opposite leg, this 2-inch, divided by the adjacent, this 3.5 inches, is the same ratio as the pitch, that is the linear distance moved, compared to the circumference, the distance moved on the outside of this circle. And we're going to take advantage of that proportion. So tangent of theta is opposite over adjacent. That also equals the pitch divided by the circumference. So you set 0.577 equal to the pitch divided by the circumference of your pin right here. Looks like my pin's diameter was 3/16. That gives you a circumference of 1.18 inches. And you just multiply that ratio by the circumference to get the pitch. And then the sort of magic moment at the end of the lab is to, physically measure the pitch. See, basically the thickness of my finger, the width of my finger is the pitch, the linear distance moved for one rotation. I predicted 0.68, and when you put a ruler on it, it's pretty close. All right, so that's experiment number 1. Pardon the scrolling. Experiment number 2 is to actually not make some threads with a paper right triangle, but analyze a househole screw. I found a C-clamp, you can find a nut and a bolt, whatever. There are all sorts of threads surrounding you. And it's a pretty simple exercise. You're going to count the number of turns you apply to this screw and see how much linear distance. For the clamp, it's this. So how much linear distance, see how the clamp is opening up, do you get for so many rotations? I had to turn this thing 50 times in order to have the gap open up 3.125 inches. So 50 times the circumference of this thing is 58.9 inches. So that's the definition of pitch. The motion, the linear motion divided by the circumferential motion or tangential distance traveled, that's the definition of pitch. So 3.125 divided by 58.9 is 0.05. Again, I don't really have the proper tool to measure this pitch. Measuring a 20th of an inch in between these threads would be kind of tricky. I do have a fancy set of calipers at school, but the inverse of pitch is the threads per inch. And so the inverse of 0.05 is obviously 20. So I predicted this to have 20 threads per inch. Sadly, when I tried to confirm that, I got 16 threads per inch. So I don't know. There's something fishy in my calculations. Like I literally counted 16 threads per inch. I don't know. Back to the drawing board. I got to double check my measurements. Thanks for watching. See you in the next video.